Okay, thank you very much. So finally we got to the last lecture. I'm very much surprised that the room is still crowded. So this probably means that the content was not difficult enough. And so, okay, the last lecture is devoted to two very much interconnected subjects, which are nonlinear Calderón-Zygmund theory and nonlinear potential theory. So if you drop the word nonlinear on both of the lines, then you get Calderón-Zygmund theory and potential theory, which are classical linear objects. And as you probably know, the main object of Calderón-Zygmund theory is given by the following problem, is that you get a linear elliptic or parabolic equation of this type, and then you know information, you a priori know information on the assigned data, which is f, and then you want to retrieve information on u. So historically speaking, this has been done in several ways, where L is a linear operator, and the usual scheme is the following thing: as LU is linear, then you get a fundamental solution. Fundamental solution has a few properties, but the fundamental solution allows you to express the solution U as a convolution, so as the image of an integral operator of f, and then this integral operator has certain properties. It's typically involving a kernel with good properties, and therefore you forget that U is a solution, and you just analyze the mapping properties of such a linear operator. The paradigm of this situation is given by the following Poisson equation. Essentially, you're assigning where the Laplacian is, and for instance, what is the equation telling you? The equation telling you that the Laplacian, that dimensionally speaking counts as second derivatives, is equal to f. So you assume that the second derivatives are where f are. So you want to commute the trace of the Hessian in the whole Hessian. And a typical example of Calderón-Zygmund theory is that if you know, for instance, that this belongs to LQ, then this tells you that the whole Hessian belongs to LQ for every q larger or equal than plus infinity, while the two borderline cases fail by counterexamples. So how this is typically done? This is typically done by using the fundamental solution. That's the Green function. The Green function for this equation has the following form. It is minus 2 minus n for n larger than 2. Otherwise, it's minus log for n equal to 2. Once you get the Green's function, then the solution can be expressed as the convolution of the Green's function with the function. Okay, there are situations where you can justify this in a rigorous way, but that's more or less the whole content. And this is actually an integral operator, and this integral operator is proved to send LQ into LQ. This is the content of the classical Calderón-Zygmund theory. And typically, how do you prove this? You prove by differentiating twice. So you get the second derivatives are, say, with this guy. The second derivatives of the Green's function are like this. Well, it's actually not exactly this. There are some coefficients here. So these are called singular integrals. Why? Because essentially, if you look at this object doesn't belong to L1 locally. It belongs to Marcinkiewicz one, so to weak L1. So it's non-integrable. But what it saves you and allows you to tell that this operator sends LQ into LQ as long as Q is far from plus infinity. And one is that there are hidden cancellations in this kernel, and cancellations are the infinitesimal information that allows you to catch the borderline case. This is the first type of a way of reasoning that has become, since then, typical in a linear analysis. So whenever size estimates are not okay, so you look for cancellations. And this is typically when you do consider, for instance, harmonic maps, systems with critical growth. Whenever size estimates are not sufficient, then you have to look for cancellations. And so these are linked to the structure, to the peculiar structure of the problem. In other words, when you get this guy, you shouldn't do this. But you should exploit the difference. That's the basic fact. Okay, this of course works because you have a, okay, there are nowadays plenty of ways to prove this. For instance, the typical Calderón-Zygmund theory is to analyze the exit time argument that allows you to decompose the mapping properties of this nonlinear operator. And this is the classical Calderón-Zygmund approach. Another approach is by interpolation, is given by Campagnato and Stampacchia. And, but okay, everything is now based on the fact that you have a representation formula. So the representation formula is the thing you like starting by. After that, you can then do other reasoning. So you have to have a representation formula, or you have to have linearity of the operator. Okay, but now, and the same thing, of course, can be done for equations like this, where this is obviously minus divergence of the gradient, and this tells you that, and for these equations, you have the following thing, which is easily justifiable as any first-year calculus student in engineering would do. How would a calculus student in engineering would get this result? By simply doing this, and that's and then he would get the result. Actually, this is called dimensional analysis. So the first-year calculus students in engineering, they do these things. Then when they grow up, they get much more scientific background, and then they still do this, but with the words dimensional analysis. And okay, and how do you get this? It is very simple. You get u of x is equal to gx minus y, f of y, dy. So you want to get the first derivatives, so you differentiate under the sign of integral. But actually, this is not f, this is divergence of f now. So you integrate by parts, and this is once again a singular integral that tells you that the gradient is where f is now. Okay, so let me concentrate just on this equation, which is easier to display what I'm going to talk about. So now the point of nonlinear Calderón-Zygmund theory is that you want to translate these informations to a nonlinear setting. So for instance, what happens if you have the P-Laplacian operator that we have been dealing with in the last lectures, and you do consider equations like this, that for instance, just for simplicity, you can display in the following way. So you would naturally expect a statement like this. And this would reduce to the usual Calderón-Zygmund statement when p is equal to 2. Oh, sorry. For q larger than p minus 1. Why p minus 1? Because if you look at the divergence form of this equation, which is this one, then you see that in order to give sense to this distributional formulation, which is satisfied for every c infinity omega, then you need that this is integrable and that this is integrable. So the starting point is that du and therefore this would be the Rada statement. So the first observation you get is that in order to give sense to the distributional solution, you don't need a solution which is in W1P, which is a natural space associated to the operator, but just you need a solution which is in W1P minus 1. In general, these are called very weak solutions or infinite energy solutions. To distinguish them between those solutions that belong to the classical space W1P, which is naturally associated to the problem. And these are so-called energy solutions. It is very important to distinguish between the two types of solutions, because while for energy solutions the situation is well clarified, and of course let me point out that I'm now looking for local estimates. For very weak solutions, the situation is not well clarified. And of course, eventually, you also want to deal with a parabolic problem. Which is this one. So let me say that for energy solutions, the situation is clear and has been the main work of several authors. And in particular, we have the following statements. Of course, I'm dealing with this equation as a prototype, but everything I'm going to talk about holds for more general equations that are modeled on the P-Laplacian equation. So the first results, the local results, are due to Ivagnez and Di Benedetto Manfredi. And what are these people proving? They hold even for the Laplacian system. And what they prove is that if F belongs to LQ, then lock, then du belongs to LQ lock. And you can even achieve a borderline case when F belongs to BMO, sort of limiting space of LQ spaces, then the gradient belongs to LQ. But this holds when P is larger than 1. And they start from energy solutions. Of course, you would like to go up to the straightforward way to P minus 1. And, but this is still an open problem. And the only results I know are due to Lewis, John Lewis and Ivagnez's Bordone. And they are able to do this up to P minus epsilon when this is a universal epsilon that is independent of the solution. But it is not clear how to go from epsilon up to 1. So what is the main technique of these papers? Is based on a maximal function technique. And actually, the maximal operator is used as a local replacement of singular integrals. Essentially, you know that maximal operators, and especially sharp maximal operators, are used to control singular integrals up to a certain extent. And so the approach of these authors is that they replace the representation formula via local regularity estimates for certain homogeneous problems. And then after a local comparison to solutions of the homogeneous problem, that is when the right-hand side is 0, then they use the maximal operator to patch up the information and to recover it globally. That's what they're doing. Eventually, another approach has been developed by Caffarelli and Peral, we're probably not aware of these papers, and they developed another approach to local estimates, which is also very nice, and it is still based on the use of the maximal operator. And eventually, Krylov, in the parabolic setting, in the linear parabolic setting, developed yet another approach, which is essentially very close to this Ibáñez and Di Benedetto Manfredi. Probably also Krylov didn't know, was not aware of these papers. These approaches have been developed at length up to the boundary and with very rough coefficients in a series of fine papers by Bune, Bang, and several other collaborators. And they also get very Reif and Bergame. And finally, all these approaches, they work in the elliptic setting, but they fail. They fail in the parabolic setting when p is different than 2, because essentially something like intrinsic geometries appear. In a few words, what you see is that this operator is not homogeneous, because when p is different than 2, this case like 1, this case like p minus 1. And so in order to rebalance certain homogeneity properties, because regularity is a matter of homogeneity, right? If you want to iterate things, you should iterate homogeneous estimates. When things are not homogeneous, you have to find the suitable domains when estimates become homogeneous. So you have to go back to homogeneity, and this is done using so-called intrinsic geometries. This is a general principle. For instance, if in other words, every operator has its own geometry where it becomes like the Laplacian. Here you use intrinsic geometries, that is, you use cylinders, parabolic cylinders, which are adapted to the geometry of the solution. For instance, in Monge-Ampère, you use sections. In the Heisenberg group, you use, let's say, intrinsic balls dictated by the Carnot-Carathéodory metric. But the thing is always the same. But since now you can only use balls that depend on the solution itself, then maximal operators are ruled out. And then together with Emilio Acerbi, we developed another approach, which is completely, which is nowadays appeared in the literature as maximal function free approach, that essentially it's completely handmade, has no harmonic analysis tool inside. Of course, I have nothing against harmonic analysis tools, but if they do not work, they should be replaced by something else. And for instance, if you go back to the usual scalar case, to the usual linear elliptic case, then you can get a fast proof of the Calderón-Zygmund theory using just mean value property of harmonic functions and Vitalis covering in less than 1 page. So this is a maximal function free approach where we were able to prove the same thing for the parabolic setting. So what we proved is that also in this case, when p is larger than 2n over n plus 2, which is a lower bound which is necessary, otherwise the diffusion is not enough in this equation, then f belongs to a q implies du belongs to a q. There are then several possible, of course, once again, q is larger than p. Of course, there are once again several possible variants. You can add coefficients, continuous coefficients, DMO coefficients, DMO coefficients. But the essence is essentially that now, in the nonlinear theory, fundamental solutions play no role anymore, because you cannot obtain general solutions by convolution with fundamental solutions, and then you do everything by hands without using representation theories. Okay, so this is so the picture for energy solutions is therefore rather complete, while the open problem remains for very weak solutions. That is, solutions that are not in the Sobolev space, which is naturally associated to the problem, which is W1P. So this happens for right-hand sides in divergence form. But when the right-hand side is in non-divergence form, then you can do much better. And therefore, I will present a theory that now intersects with nonlinear potential theory. And I will present something which is nonlinear Calderón-Zygmund theory for so-called measure data problems. So now we switch from right-hand side in divergence form. That is, right-hand side whose form is in the divergence of something, to a right-hand side which is not in divergence form. And of course, when the right-hand side is not in divergence form, the worst possible case is that it's not even a function, it's a measure. Therefore, I'm going to go to the realm of measure data problems. Okay, measure data problems are defined in the following way. So you get divergence A of du. Of course, I can also consider things that are depending on x, but there is no point in being so much general. Just think to the P Laplacian. And on the right-hand side, I have a measure mu. Okay, as assumptions that can be for several results also very much weakened, I will use the following assumptions. So the following assumptions are are the following ones. A of z is growing as z to the p minus 1, and the derivative of z, actually, let me do the following. Let me do directly this, which is stronger, and then the derivatives of this are growing as c to the p minus 2 psi squared. The prototype being, of course, given by the P Laplacian operator, which is the following one. Okay. Okay, of course, once again, the distributional form of this equation is the following one. And these solutions typically come from solving Dirichlet problems like this. Now, it's a matter of fact that distributional solutions are not good for deriving estimates, because essentially you don't know where to test with. You don't know where the solution is. And on the other hand, you want to prove existence for this. Therefore, there are several ways to argue, and I will just follow the most natural one that gives you a notion of solution which is stronger than just the merely distributional one, and that allows you simultaneously to get existence of solutions. And that's the solution, that's the notion of SOLA, solutions obtained by limiting approximations. So essentially what you want to do, you take a smoothing sequence of mu, which is weakly converging in the sense of measures to mu, right? And you define, you solve these problems, and then you pass to the limit. And then I will also define the more general notion of local SOLA, saying that u that belongs to W1P minus 1, actually, it's a local SOLA to that problem if there is existence of a sequence of measures that are in L infinity, which is weakly converging in the sense of measures, weakly in the sense of measures. And such that U, n is converging weakly in L1, in W11. And finally, such that the limb sup of the total variation on every ball is less than or equal than this. Observe that when all the measures are positive, this is automatically implied by the weak convergence. Otherwise, you have to prescribe it. So for me, a sola is just something that can be obtained like this. Okay, okay. What do you expect on such solutions? Well, if you look at the so-called nonlinear Green's function, the fundamental solution to this problem, where this is the direct measure charging the origin, well, then you will see that the Green's function is something like that. As you see, for p equals to 2, this coincides with the usual Green's function. Otherwise, it is what it is. Okay, what's the, okay, it can be proved. Well, in a certain sense, when you prescribe the right-hand side being a direct measure, this is one of the worst measures you can work with, because everything is concentrated at one point. The idea is that the more the measure spreads, the better the solution it is. If the measure becomes if the measure concentrates everything at one point, then there is really a problem. In fact, if you want to test your regularity results, then you should look at the integrability of these. It is very easy to see that the gradient of this solution belongs to Marcinkiewicz n p minus 1 n over n minus 1. So these are the right spaces to understand the sharp integrability of measure data problems. Let me recall you that the Marcinkiewicz space is given by the m gamma, or gamma larger than 1, larger or equal than 1. This is also called weak gamma, or the Lorentz space L infinity. Well, f belongs to this if and only if the sup of this quantity is finite. So you prescribe the decay of the level sets, and you put this weight. These are spaces which are slightly larger than L gamma. Let's say they tune fine properties. So it's L gamma, it's strictly contained in M gamma, which is strictly contained in this. You can easily come where this definition is coming from, because you immediately see that if you take a function which is in L gamma, then you get the level set by Chebyshev. This is less than or equal than f the gamma 1 over gamma, right? And therefore, the sup of these guys are bounded by the L gamma gamma. So if f is in L gamma, it automatically belongs to M gamma. Otherwise, you take the left-hand side and you prescribe that it is finite. And that's where a way to get rapidly a justification of this definition. Okay. So the basic, a basic existence and regularity result for measure data problems is the following. One is due to Boccardo and Galloway. And it prescribes that every local sola, it's just that locally belongs to MP minus 1 and minus 1 block. The local version of this space is obviously having the intersection of the level set on small subsets. In particular, that's the same to require this. So what is the object which is under the sign of divergence for the P Laplacian belongs to Mn over n minus 1 block. The existence of sola is clear. Their uniqueness is still an open problem. You can find very few cases where you can prove uniqueness. As a paradox, the worst case is one of the very few ones where you can find uniqueness. They become unique when the right-hand side belongs to the dual space. And therefore, an object of interest for the right-hand side is given by the situation when you want to prove, you want to analyze a situation when the right-hand side is not in the dual. Because when it's in the dual, then you can write down by definition, by something, which is divergence of G, and G is in LP, and then you go back to the previous theory. So the previous theory of Ibanez, Di Benedetto Manfredi, and other people then covers the case when the right-hand side belongs to the dual, because then you can write it down as something which is the divergence of this guy, and this belongs to the right space. You can work with the other in the other range. So in particular, you know that if the right-hand side is not only a measure, it's a function, if the right-hand side is a measure, is not a function, then the big spaces you want to work with is the condition that this belongs to this when Q is less than P star prime, because you know that the Sobolev duality, where this acts against Sobolev functions, if f belongs to W1P, then you can do some sense. You can do Hilder's, and then this is P star, and this is P star prime. So if you are here, then this belongs to the dual, and P star prime is the Sobolev conjugate of NP over P minus N. And let me also remark that the case of relevance here is given by P minus N, because then for P larger than N, points of positive capacities, and all the functions belong to the dual. So here really the range of exponents of interest is the following one. So this is NP and P minus N plus P, if I remember correctly. Let me do this. Minus N plus P, yes. So we are interested in this theory, and as long as this is true, then there is this other result of Boccardo and Galois that states that if mu belongs to LQ, for Q larger than 1 and less than P star prime, then you get the exact analog of Calderón-Zygmund theory for the gradient, not for the second derivatives, and this tells you that this has to belong to NQ over N minus Q. Why? Let's make dimensional analysis out of this. You get that the divergence of u to the P minus 2 u is belongs to LQ, right? Now trade the divergence with the gradient. Trade this with u to the p minus 1. If the derivative of this guy belongs to LQ, then this guy will, by Sobolev embedding, belong to this space. More in general, for these problems, there's a more general approach that allows you to prove the following thing, and this is developed in a paper of mine. You can actually estimate the size of level sets of the gradient with the level sets of the fractional maximal operator of the measure. Well, the fractional maximal function operator is the following thing. What is the maximal operator of a function f or of a measure? You take these guys, you take the sup over these averages, and then you get a maximal operator at one point, at the point x. Okay? How do you get the fractional m1? Then, well, you correct this with just rho. So this has a further smoothness property. Just kills more and more. This is a smoothing operator with a better smoothing operator than the maximal operator. So this is called the fractional maximal operator. So you can control the level sets of this guy with the level set of these guys in a sharp way. And this provides a unique approach that allows you to get back not only these results, but results in all possible rearrangement invariant function spaces. So this also holds for when you get measurable coefficients and gives a unified approach to this theory of measure data problems that in fact allows you to get all the previous results plus borderline case in a unified way. So what you're doing, you look at the scaling of the problem, and you see that when you scale this by rho, this scales like rho, the same thing. And then you can control the gradient, the level sets of the gradient, with the level sets of the fractional maximal operator. As the mapping properties of the fractional maximal operators are known, then you can immediately infer where the gradient is. Of course, this is a very rough way because there's an additional term that prevents you to go beyond LP integrability, because otherwise the result would be false. But essentially, the essence is that you can control the level sets of the gradient with the level sets of the maximal fractional maximal operator. This has been done in the interior. Then there are several papers by, for instance, people by Pook and other people that they go up to the boundary, but the essence is always the same. So this, you see, it goes towards an estimate of singular integrals type, but you use a fractional integral. So the approach introduced in this paper, I think it's from 2010, is that you can control the level sets of the gradient with the level sets of the fractional maximal operator, and then you forget that the gradient is a solution, and you just look at the mapping properties of the fractional maximal operator. So this is, in a certain sense, a first type of decoupling the solution from the data via a fractional operator. So this is a level set estimate that is a global estimate. And later on, we shall go through another version of this, which is the gradient potential estimates, which is a pointwise estimate. Because we will see that the fractional maximal operator can be controlled by the Riesz potential. And when you go to the Riesz potential is a more powerful operator because it involves not a sup, but a series. And when you go to a series, you can pointwise estimate the gradient by the Riesz potential. We will see later. Okay. This as far as the integrability of the gradient is concerned. And now, let me briefly mention some higher order regularity, which can be considered, let's say, you see, this is a fractional operator, so this can be considered the first analog of a fractional integral estimate. And now let me go to the analog of the singular integrals. That is when you really want to look for the ghost of the fundamental solution. Fundamental solutions cannot be obtained here, cannot be used here, because the problem is nonlinear, so convolution doesn't produce new solutions. But now the ghost of the fundamental solution is hidden in the estimate. Because the regularity estimates for these problems, they encode the properties of fundamental solutions. And in fact, this is well known. There are famous people like Gruther, Widman, and then several other developers that uses regularity estimate to infer the good properties of fundamental solutions. Okay. The point is the following one. Now, we do not look to integrability properties of the gradient, but we look to differentiability properties of the gradient. Therefore, we go back to this problem, and you see that if mu belongs to LQ, then it is known that du belongs to W1Q if mu belongs to LQ, but this is true as long as this is larger than 1. Okay. The case Q equals to 1 fails, but on the other hand, for general elliptic equations of this type, we have that the properties of the fundamental solution are reproduced at the level of integral estimates, because you know that the gradient belongs to Marcinkiewicz. The gradient to the p minus 1 belongs to Marcinkiewicz n over n minus 1. So you see that you have all the integrability you might like to have, while you have no other property on the gradient. Also, the equation is of second order. So you would expect a differentiability result of the gradient. Well, here you just have integrability. Let me point out that this is under these assumptions and guarantee coercivity. It's the same that requiring this. So we look for an intrinsic formulation that just looks at what it appears under the sign of divergence, intrinsic formulation. Okay. So the gap between integrability and differentiability had remained open for a large while. And the first result is a theorem which is stated in a paper of mine. And that tells you the following. Let's start by the case p equals to 2. So you know that du cannot be in W11, but you can still prove that this is in W sigma 1 for every sigma less than 1. So if you cannot be in W11, you are in W sigma for every sigma less than 1. And let me recall you the definition of fractional Sobolev spaces that I introduced yesterday. This means that that this quantity is finite. Okay, of course, everything is local here, local, and that this quantity is finite. For every subdomain A. This is sigma. And this is sharp because, of course, you cannot get this guy. For the case, let me just consider the case p larger or equal than 2 for simplicity. For this case, you know that already when the right-hand side is 0, the gradient is non-differentiable due to the fact that the equation is degenerate. And then you can prove that the gradient belongs to W sigma over p minus 1, p minus 1, for every sigma less than 1. Once again, for every sigma less than 1. is this sharp? The result is sharp because if you look at the Green's function, that's exactly the best result you can get in terms of Sobolev spaces. That's another way to understand why you cannot achieve sigma equal to 1. This is already clear in the case p equal to 2, because otherwise this would get you 1, right? But fractional Sobolev spaces, they have their own embedding. In particular, this embeds into this. And if you would have 1 here, then you would get the gradient would belong to n p minus 1, n minus 1, which is forbidden by the fundamental solution. But you cannot achieve that. But now let me recall you this intrinsic formulation. This intrinsic formulation has something which is very suggestive, because if you look at this equation and if you look at the integrability result first obtained by Boccado and Galloway, and in the case actually p equals to n, and as this remained open for a while until it was settled by Doltzmann, Ungenböller, and Müller in a long paper, the case p equals to n. So you see, there is something that allows you to reproduce, to write down the best integrability result while no p is appearing here. See, there is no p appearing. In some sense, this result allows to take this equation and saying that you can trade the divergence with the gradient and get embedding. In the same paper, there was another result which was conjectured in this paper. So the conjecture was the following thing, is the following one. So let's take this equation and let's treat it as a linear equation. Well, let's imagine it's linear. So let's imagine that A is the identity. Then you go back, is the gradient of something, let's say. And you go back to this, and you would get that this something is in W11, almost W1. So the conjecture I had in that paper was that A of the U for every sigma less than 1. And this would imply both the results. This was conjectured in that paper and finally proved 10 years later. Now this conjecture became a theorem by Avelin, Cusi, and myself, a theorem proved last year. Well, it actually proved 3 years ago. It appeared this year. And this is the final point of differentiability. That's the highest possible regularity you can get. If you think, it's a very surprising fact, because this tells you that no matter the equation is nonlinear and degenerate, it actually can be read. So this equation, you see, it's a nonlinear equation in the gradient, but you can use it, you can frame it as a linear equation in a nonlinear vector field of the gradient. So this equation is now becoming linear in the vector field A of the U. And this comes along with a suitable Cacciopoli type estimate, which is the following one. This is a ball. There's a ball. And that's the best possible scale. B rho, BR. for every ball, you get the following Cacciopoli type estimate. You see the perfect scaling and cancels with an integral. Rho is here, and then you get what you get. So this is the ghost of singular integrals. So that's the ghost of singular integrals. Ghost of singular integrals. So the surprising fact here is that you get a nonlinear equation, and then you treat it as it were linear. So therefore, if there's a ghost of singular integral, if there's a ghost of singular integrals, then there should be a ghost of fractional integrals. And now we go to the other ghosts, and we go to nonlinear potential theory. And when we go to nonlinear potential theory, we go to even more surprising results, because now we will see how, in a certain sense, to reduce the whole regularity theory of nonlinear degenerate equations to the regularity theory of the Poisson equation. Okay, so therefore, let me go back to this to the Poisson equation. And the Poisson equation is something for which you get essentially two estimates via fundamental solutions. You put in Rn, and the first estimate you get is Ux is less than or equal than Rn d mu y, x minus y, n minus 2. Let me consider for simplicity n larger or equal than 2, strictly larger than 2. And this is the so-called I2 Rees potential evaluated at x. This is y. So this comes from the representation formula via the fundamental solution. That's straightforward, because that's actually the size of the Green's function. While for the gradient, after differentiating under the sign of integral, you get a similar estimate. But of course, since the gradient is a higher order object, then you get a less regularizing kernel. And this is this guy. And this is I1 mu of x. Okay, so these are a straightforward consequence of the fact that you can represent solutions via convolution with via the fundamental solution. And of course, these are apparently ruled out in the nonlinear case. That's not the case, in fact. Okay, so I will now consider local sola to this equation. And actually, as long as the estimates for u are concerned, I can even allow a measurable dependence on x for u estimates, on u, but not on du. And of course, the prototype is always the usual one. Equal to mu. Okay. And finally, since I'm dealing with local estimates, let me introduce a suitably localized form of Rees potential that allows you to get the convolution not on the whole domain, but just on small balls. This is so-called the truncated Rees potential. The truncated Rees potential is simply defined as follows. You get I1 so this is an integral, actually. You rho over rho, you get the measure, you get This is rho x n minus 1. And you can easily prove that this object, this object is less than or equal than the usual risk potential at the point x. It's just a truncated version. It's much more, in a certain sense, you are reducing the domain of integration over the ball BR. So this is a suitable object to get local estimates. Okay, so, and of course, you can do this. This is the beta. If this is the beta risk potential, and the beta risk potential is defined in the usual way. The beta risk potential, beta risk potential is the global risk potential, is the usual one. It's a fractional integral because beta is supposed to be larger than 0, so it kills a bit of singularity and allows the kernel to be locally integrable. Well, okay, of course, if you look at the P-Laplacian estimates, estimates for the P-Laplacian operator, then these estimates cannot hold. And they cannot hold for the simple reason that they do not respect the scaling of the equation. In this equation, the left-hand side scales like p minus 1, and this scales like 1. So only for p equals to 2, then when you go back to the Poisson equation, then these estimates can be expected. So if you want to get an analog of these estimates, then you correct the risk potential with the scaling of the equation, with the scaling deficit of the equation. And you introduce the so-called Wolf potentials, although they were first introduced so-called Wolf, but they were first introduced in a fundamental paper by Having and Mazia in 71. Actually, Mazia is the real founder of nonlinear potential theory. Okay, what are risk potentials? Wolf potentials. Wolf potentials are defined similarly. You get the usual story, 0 over rho, so that's the hard measure. You get mu b rho x rho n minus beta p, and you just correct it with p minus 1, which is the deficit scaling of the equation. So these are the orthodoxy of nonlinear potential theory tells you that whenever you go to nonlinear problems, Wolf potentials replace risk potentials. For instance, they were used for the first time quantities like this, which are actually series, because you can write down a series of these powers. Were introduced by Mazia to prove some sufficiency part of the Wiener criterion for the P-Laplacian operator, and have been used a lot in the literature. So the orthodoxy is that whenever you get, you go to linear problems, risk potentials should be replaced by Wolf potentials. And let me also observe that the mapping properties of the Wolf potentials are completely well known, because you can there's an inequality. And from now on, once again, let me recall you that for simplicity, I will just consider the case p larger or equal than 2. Then you can prove an inequality like this. You can estimate this guy by a nonlinear iteration of risk potentials. If this is the classical risk potentials, then you can prove the following inequality. So you can control the Wolf potential by a nonlinear iteration of risk potentials. The one you're seeing on the right-hand side is called Having-Mazia potential. And actually, for p larger than 2, this becomes a double-sided inequality. And of course, since the behavior of the Riesz potential is well known, also the behavior of the Wolff potential is well known in every reasonable rearrangement invariant function space. So once you know the mapping properties of the Wolff potentials are well known, well clarified, let's say. Now, the first interesting result, which is a fundamental result, is a theorem of Kilpelangen and Mali. That states, surprisingly, that if you get, okay, this can be explained for several solutions, but take it as a uniform a priori estimate for where everything is smooth. But for solar, it definitely works. Then you can pointwise bound Ux by the Wolff potentials 1p mu xr plus dr uy dy. What is W1p? W1p is this guy. And you can see that for p is when p is equal to 2, this is exactly the Riesz potential. So this tells you that although, of course, there are constants implied here, and this is an average, and of course that it is necessary to have this object, because you know on the points where this is finite, when capital R goes to 0, this goes to 0 being an integral, therefore you get u less than itself. Otherwise, you can let capital R goes to plus infinity, and under suitable assumptions, these disappear, and you get the global estimate. So this is something that allows you to get an estimate which is a typical consequence of the fundamental solution representation, while there's no fundamental solution representation. You can get directly the estimates without passing through the fundamental solution. But now, this is from 91, I think. And now there were essentially two open problems. This is for scalar equations. The open problem 1, what about du? And open problem 2, what about the vectorial case? Essentially, what about the P Laplacian system? And let me recall that the existence theory for measure data, when you have the P Laplacian system, for general system, this is not known, but for the P Laplacian system, it is a paper by Doltzmann, Hungenmuller, Müller. Okay, now I will present the solution to these two open problems that actually arrived more than 15 years later. Okay, what is the problem with the gradient? Okay, let me recall you that that for the case of systems, even this estimate was an open problem. Okay, what is the problem? What is the problem with the estimate? The problem is that if you want to get a gradient estimate, then you unavoidably, and under the usual conditions, under the usual techniques, you unavoidably have to undergo the differentiation of the equation. That is, you take the equation, you differentiate, you prove estimates for the second derivatives, and then you do Moses iteration for the gradient. That's how you usually do, right? For instance, when and you have to do this actually because if you want to have a gradient estimate, then you really have to do this. For instance, how do you prove that a gradient is bounded in this case? Then the equation in the weak form is the following one. You differentiate it. When you differentiate it, this becomes first derivatives of the u, the s u d phi for every s, right? But then this is the solution of a linear elliptic equations with bounded and measurable coefficients, at least for when p is equal to 2. And then you can apply the George's theory. But of course, you have to make the first step. So you want to differentiate the solution. But on the other hand, when the right-hand side is a measure, you cannot differentiate the equation. Because even for the Poisson equation, you do not have first derivatives. Nevertheless, the first result to this estimate is in a paper of mine, actually written in 2008. And tells you the following. It's a theorem by myself. So you see, here the real problem is not really treating the degeneracy, which is an additional remarkable problem, but it's really passing from linear to nonlinear, because you want to get a linear estimate for a nonlinear equation. And so this is a paper of mine, and it tells you that you can pointwise estimate for p equal to 2, so for general equations like this, you can pointwise estimate by the Rees potential like this. So in particular, when you are on the whole Rn, and this decays reasonably at 0, you can pointwise bound dux by the usual Rees potential exactly as it were linear. The implications of these are very wide, because once you get this estimate, the whole regularity theory on the gradient can be reduced to the one of the Poisson equation. You just forget the whole estimates, all the gradient estimates, for instance, in the books by Lagrzynska, Ural, Seva, and all these classical facts, they are covered in one shot for the gradient. Okay, the first technique is particularly peculiar, because what I did to give the first estimate was the following thing. Well, let me recall you that p is equal to 2. So I first notice from my previous paper that you can get that this guy's gradient is differentiable. So, in a sense, while in the usual case you apply the George's theory to the gradient, that is, you do truncation of the gradients and then you do the Georgi or Moses fractional iterations. Here I write down a Cacciopoli type inequality and no local Cacciopoli type inequality for truncations of the gradient of this type. Once you get this, and you do this in a very delicate way using a sort of nonlinear little Paley decomposition, where the atoms are, the atoms you're using are not harmonic functions, but solutions to homogeneous equations, then you run a fractional version of the George's iteration. Because we have seen from the first day that the George's iteration is based on a geometric iteration. So any exponent in the geometric iteration is good to converge. So while the George's iteration uses the exponent coming from Sobolev embedding theorem, the fractional version I introduced here uses the exponent coming from the fractional Sobolev embedding So the convergence is less speedy, but it's still a convergence. At the same time, well, while the previous, this approach, of course, it's thought to overcome the fact that the equation is non-differentiable. So the real strength here is to get that to get a fractional differentiability and a fractional Cacciopoli inequality for truncations of the gradient measured in a fractional space. And then the second step is this fractional iteration of the Giorgi's version. And the second step has been independently introduced by Caffarelli and Vasseur in another paper for fractional operators. They are fractional operators, and therefore they first deduce the Cacciopoli inequality with that in their setting is straightforward because you have a fractional operator, while here you have to really fight for that. And then the second step is that they introduce a fraction of the Giorgi's iteration, which is in the spirit very close to this one. So this is probably less known, this fraction of the Giorgi's iteration, because it has not been developed in the natural setting of the fractional operators. There you have a fractional operator, so you have to run naturally a fraction of the Giorgi's iteration. Here you have a second order operator, so an integer order operator, but a lack of differentiability. So the trick is that you get this. Okay, this is as long as p is equal to 2. Now let's go to the case p larger than 2. Well, now the orthodoxy of the theory would tell you that you have to use Wolf potentials, and in fact, the first estimate via Wolf potentials has been obtained by Dutzer and myself. But now the surprising fact is the following one. The surprising fact is that in this case, linear potentials come back into the play. Linear potentials. And what you actually come up with is the following magic fact. So if this holds for the Poisson equation and holds when p is equal to 2, what happens for p different than 2? It happens actually nothing but this. You just do this. So this apparently magic fact allows you to reduce the whole theory once again of elliptic equations that are now allowed to be degenerate to the theory of the Poisson equation. So in particular, all the estimates you might like for the model problem, P Laplacian of u equals to mu, all the estimates of Boccardo, Galois, Ibanez, Di Benedetto, Manfredi, Talenti, Lagichenska, and Alceva, all the gradient estimates are now covered as a corollary because actually the equation has been completely linearized. Why is this so? Because of the same thing I told you before. The equation can be seen in two ways. It's a nonlinear equation in the gradient, but it's a linear equation in a vector field, in a nonlinear vector field of the gradient. So you get this guy. You formally apply the Riesz potential to both sides. But the Riesz potential is an integration, so it formally cancels a divergence, and the equation is telling you that you should be able to prove, to estimate A of du by the Riesz potential. And that's the content of two papers. For p less than 2 by Dutzer and myself, and for p larger than 2, which is the most delicate case, so I'll state for the case p larger than 2 by Cusi and myself. And for p less than 2, p larger than 2, then you can prove the following estimate. And equivalently, because of the coercivity, the same thing. And in particular, when you have suitable decay assumptions, then you get this inequality. So this gives a surprising solution to the first open problem. Surprising because although you are getting a linear problem, although you're getting a linear problem, you're coming up with a linear estimate that reduces the whole theory to the linear theory. So the nonlinear theory has disappeared, and now the linear theory goes back. What about the second problem? The second problem has a more recent solution, and we have essentially the same two results in a new paper, which is probably the best paper of this series, called Vectorial Nonlinear Potential Theory. Appearing in GEMS this year. And this contains the same estimates both for U and for the gradient. So as a consequence, all the missing theory, all the missing lower order Calderón-Zygmund theory for the P-Laplacian system that was well established and refound as a corollary in the scalar case now can be built in once. So once again, all the estimates in the classical papers of Talenti, which are scalar, they can be obtained in the vectorial case. All the estimates by Boccardo and Galloway, that they were scalar, Boccardo, Vasquez, Miura, Galloway, all these people that have been working on these problems, now can be upgraded to the vectorial setting, and so forth. The proofs are very much different, and they combine something coming from geometric measure theory and linearization and partial regularity, and in particular Uhlenbeck's techniques with nonlinear potential theoretic techniques, but the results are the same. The results are the same, and you can completely linearize the theory. So finally, this is true up to the level of the gradient size, but actually the techniques can be carried over to prove also oscillation estimates. And let me tell you just one corollary that holds both in the scalar and in the vectorial case. So essentially what you're doing here, you are replacing the missing fundamental solutions with pointwise linear potential estimates, giving a completely nonlinear approach to all kinds of problems you might like to have. So let me point out a similarity between this estimate one, let's say the estimate, the fractional integral, and this estimate, the singular integral. What is the similarity between these two estimates? Question, do you see P, the exponent P, appearing in the statement? The exponent P is not appearing. The exponent P is not appearing. And so that's the real strength of these estimates. They completely linearize the problem, and they are able to read, to give you the problem, because the problem is now not a nonlinear problem in the gradient, but is a linear problem in a nonlinear vector field of the gradient. And in fact, you don't need to have P growth. You can allow more general operators like this. And getting exactly the same thing, while this G is not polynomial now. It's just uniformly elliptic. That's a non-trivial paper of Baroni from 15. So it's a general phenomenon. You can bound exactly what you have under the sign of divergence, and by the risk potential. The estimate is exactly G of the U less than or equal than the risk potential of mu plus the average of G. Whatever G is uniformly elliptic. So no polynomial growth allowed. No polynomial growth prescribed. Just to conclude, let me tell you, as I was saying before, that these estimates also provide information on the gradient, on the oscillations of the gradient. Why? Okay, what happens when so a trivial corollary. So what happens if this belongs to L infinity. If this belongs to L infinity, then trivially du belongs to L infinity. Okay, observation. Is this condition depending on P? The answer is not, because this is a Riesz potential, and it has nothing to do with P. So the condition for the gradient to be bounded, to be locally bounded, is independent of P. This is the answer of an old conjecture by Inyawe-Altseva, who conjectured that the condition for the right-hand side, in order to allow that the gradient is bounded, should be P independent. Probably because Altseva already had in mind this linearization effect. But now we can do a bit better. What is this guy on the right-hand side? This guy on the right-hand side is the Riesz potential, so it's this quantity. In particular, whenever the integrand is, this is an integral. So if this is finite by the absolute continuity, it goes to 0 when r goes to 0. Right? Now, the question is the following. What happens if you prescribe that this convergence is uniform with respect to x? So the theorem is the following. By Kusi and myself, and this also holds in the vectorial case, is the following. If the lim is uniform, then du is continuous. So the boundness gives you the boundness. The uniform convergence to 0 prescribes the rate at which the measure does not concentrate in order to consider, in order to infer the gradient continuity. And in particular, this has a lot of corollaries. For instance, it allows you to prove a surprising nonlinear version of a classical result of Stein. And this is the last result I'm going to talk to you. Is the following one. Consider the following thing. And you want to know what is the best space f has to belong to in order to guarantee that du is C0. This is the so-called Lorentz space Ln1. And this is obtained by prescribing the decay of the level sets at this peak. This comes from, this is equivalent to this theorem of Stein that tells you that if f belongs, if the gradient of f belongs to L, if the gradient of a function belongs to Ln1, then v belongs to C0. Ln1 is a space which is somehow smaller than Ln, and it is larger than all these other guys. You know that when the gradient belongs here, then v belongs to C0 epsilon plus n plus epsilon, if I remember correctly. So this is the limiting case of Sobolev embedding theorem, of Sobolev-Morey embedding theorem. And when you apply this, you get this equivalent formulation. And now, as an example of a corollary of this condition, of this general theorem, let me observe that it's just a matter of checking the definition to see the following, that if mu belongs to Ln1, then this convergence is uniform in X. But if this convergence is uniform in X, then this is telling you that du is continuous. So you have the following nonlinear Stein theorem. Take the P-Laplacian system, and if this belongs to Ln1, then the gradient is continuous. And you get more and more corollaries. This reasoning can be pushed forward until the maximal regularity. And if you want to see more gradient oscillation estimates, you should look at two papers. These are the last two papers I'm mentioning you, by both of them by Tomokusi and myself. First paper is called Universal Potential Estimates. And in this paper, we introduce a new approach that allows you, because these estimates are allowing you to estimate the gradient with risk potentials. We will estimate the fractional derivatives of the gradient, so higher order estimates, with other risk potentials, with different Wolf potentials and risk potentials. And in particular, we shall see that the two estimates are U for U and du are two particular cases of a larger family of estimates, which is called universal potential estimates. Well, if you want to have a global overview of the theory, you can also look at a paper which is called Guide to Nonlinear Potential Estimates, or Guide to Potential Estimates. It's published on this Bulletin of Mathematical Sciences in 14. But this is actually a paper you can look at to get more information. Well, this is actually the last thing I wanted to tell you, and this is also the end of all these lectures. Thank you very much for being here. I was very happy. Thank you.